For the review today, I'm going to go through a few selected problems that are actually on your review sheet. I'm going to do a few that are similar to ones that are on your review sheet, but that are just changed a little bit. And then there are some that I'm actually not going to cover, but there will be time, hopefully, after I finish this, where you'll have time to work, and I have an answer key that you can look at, because we've talked about it before, that like watching me do it is one thing, but really you need to be able to do it. So I do want to go through a few of what I've noticed in like 9 years of teaching this as being commonly mistaked problems. However, I should be saying that that's not the right way to say it. But problems that students usually get wrong and what their common mistakes are. So I really want to address those, and then the other ones you'll have time to kind of work through. So the first problem that I want to look at is question number 5. And I want to look at question number 5 just the way it appears on your test, or review. The bases inside of those parentheses are different, so that means that we cannot combine those two things together, but we can take care of the power on the outside by giving it to everything inside. When we give a power to a power, what do we do with them? Multiply them. So that's 4 to the 1/3, and then there's a 3 outside. It's kind of hard to see up on the projector, but hopefully it's a little bit more clear on your paper. 4 to the 1/3 and 3, so 1/3 times 3 is 1, so that gives 4 to the 1st. Same thing for 5, 1/3 and 3 makes 1, so I get 5 to the 1st. So 4 to the 1st times 5 to the 1st, and that's actually something that we can evaluate and just get 20. The next problem that I want to look at is like number 6, but I'm going to change it a little bit so that it doesn't work out quite as cleanly, and see what we would need to do about that. Okay, so this is the same type of problem as number 6. But the values are changed so that it's not going to work out actually quite as nicely as number 6 does. So when we are taking a root of numbers and variables, we want to deal with each of them individually. So the first thing we're going to take care of is the number. In simplifying a root of a number, we want to look for any perfect, whatever types of root it is, that goes into that number. So we're looking for perfect cubes that go into 54. So our first perfect cube is 2 times 2 times 2, which is 8. 8 divides into 54. Okay? So we can break that down, and it would be the cubed root of 8 times the cubed root of 6. Right? Isn't 8 times... That's not 54, is it?
No,
Nope.
That's 48.
That's 48.
That's like,
okay, so 8 doesn't go in there. Then the next perfect cube would be 3 times 3 times 3, which is 27, which does go in there. 27 times 2. So then the cubed root of 27 is 3. So that's going to become a nice clean number. And that'll go all the way on the outside of this thing. That 2, there's nothing we can do about that, so that's going to stay on the inside of the root. I'm leaving some blanks there because we still have to deal with the variables. And one of our major rules, and this is the rule that you would apply to solve numbers 2, 3, and 4, is that the top is a power and the bottom is a root. So we can think of these powers and roots as being fractions and divide them out. So for x, we would want to divide that power of 7 by the root of 3. 7 doesn't divide by 3 evenly, so we want to say how many times does it go in evenly. So how many times does 3 go into 7 evenly? 2. With a remainder of 1. So the even division comes out and the remainder stays inside. So we divide 7 by 3, goes in twice, so 2 comes out, remainder of 1, 1 stays in. Y to the 4th, 4 divided by 3, goes in evenly how many times? 1 with a remainder of 1. So 1 comes out, 1 stays in. And Z has a power of 9. 3 goes into 9 evenly. How many times? 3 times. So 3 come out. Remainder of None, so none are staying in. So that would be our final answer. The next one I want to look at is number 8, exactly as it appears on your review. Number 8 is commonly given as the answer that students commonly give is the square root of 87. That is wrong. Okay. We cannot add or subtract roots that are different. To be able to add or subtract roots, they have to be the same type of root and of the same thing. So we cannot add these together when the 75 and the 12 are different. So what we need to do is simplify them individually in hopes that they will turn into the same type of thing. So to simplify a root, we're looking for a perfect whatever kind of root it is that goes into that number. So these are square roots. What's a perfect square that goes into 75? 25. 25 times 3. And what is a perfect square that goes into 12?
4.
4 times 3. The square root of 25 is 5. The square root of 4 is 2. And now they are the same type of thing. They are both roots of 3. So if I have 5 of them plus 2 of them, then I have 7 of them. Questions? Okay, the next types of problems that I want to look at are similar to that next group of problems, but I want to use some different functions that are a little bit messier. So I'm going to use function f as x to the 1/2 and g as x to the 1/3.
Wait, are we doing any of these?
We're not going to do any of those here, but during the work time you have if you want to work on those for more practice. The first thing I want to do with them, and we're not going to go through all of the operations here, but I want to do f of x times g of x. This is our first problem here. So that would be then, we're going to do x to the 1/2 times x to the 1/3. The bases are the same, so what do we do with them? Add them. What do we need to be able to add them? Common denominators. So I'm going to make this x to the 3/6 and x to the 2/6, which I can then add up and get x to the 5/6. Domain. The two questions we ask for domain are there any even roots and is there any division? Are there any even roots in this? Be careful.
Yes.
It doesn't look like there's any roots at all, right? Because there's no root symbols. But remember that a root is really a fraction exponent, and the root is the bottom of that fraction exponent. So this has a 6th root, even though it's not written that way. So there is an even root. And what does that do to our domain? Greater than or equal to 0. An even root does not allow for negatives. You can't take a square root of a negative number. And the second question we asked ourselves is there any division? No. It's just a plain x. It's not divided by anything. So then our domain will be x is greater than or equal to 0. The next one I want to think about is f of x over g of x. So it'd be x to the 1/2 divided by x to the 1/3. What do we do with powers when we're dividing?
Minus.
Subtract them. So we're going to have, again, a common denominator. 3, 6, and 2, 6. And when we subtract them, then we get x to the 1, 6. Domain. Are there any even roots?
Yes.
Yes, there's that denominator of 6 there again. So that gives us x is greater than or equal to 0. Now with division, remember we have to be careful about the question, is there any division? Because this was a division problem. We simplified it out, but it was a division problem at one point. And so we need to consider that in that original division, x couldn't have been 0 because we wouldn't have been able to divide that out then. So if x is supposed to be bigger than or equal to 0, but can't be 0 because of the division, then we end up with a domain of x is greater than 0. I want to look at one more of this type, and that's where we do our composition, f of g of x. When we do a composition, we write the outside function except not the variable. So I want to write f, which is x to the 1/2, but I don't want to write the x. So then that's just stuff to the 1/2. And we write the outside function, but we don't write the x, we leave a blank instead. Let's see. So instead of x to the 1/2, we'll have blank to the 1/2. Then in that blank goes the inside function, which is g, or x to the 1/3. Most common mistake that students will make here is they'll remember that they're supposed to have like a blank to the 1/2, but they'll still write an x like out in front of those parentheses. Okay? That x on the outside function completely disappears to become the parentheses. What do we do for power to a power? Multiply. So we multiply those together, and we get x to the 1/6. Are there any even roots? Yes. That gives greater than or equal to 0. Is there any division? No. So then that is our domain. Questions on multiplying, dividing, or composing functions? The next problems that I want to look at are a couple of these inverse problems. I'm going to look at number 15, just as it appears on your sheet. To find an inverse of a function, we have 2 steps. First step is switch the x and y. Remember, f of x means y. So we're going to change that into an x and change the x into a y. Then our second step is get the y alone again. So I'm going to do that by subtracting 3 from both sides. And then I need to get rid of the 1/3. How do I do that? And multiply by 3 and make sure that you multiply the entire equation by 3. That's the common mistake here. Students will just kind of pick and choose different parts to multiply by 3. We need to multiply everything by 3. So it gives 3x minus 9 equals, instead of calling it y, I'm going to call it f inverse of x. Now I will probably not be so picky about the notation that if you just left it at y, I will probably not take off any points. But that's one place I would really like you to try to use proper notation and emphasize that, but I probably would not take off points. I'm going to look at number 17, just as it appears on your sheet. So we're going to switch x and y. And then we want to get y alone again. So what do I do first to get y alone? Subtract 3. And then what do I do to get y alone? Square root it. Undo the square with a square root. So then I get the square square root of x minus 3 equals f inverse of x. Now technically when we take a square root in an equation, what are we supposed to have in front of it? A plus or minus, but we were also given in the problem here just a greater than or equal to 0 limitation, so that means we're really just dealing with the positive anyway, so we don't have to worry about that plus or minus. But square roots, fourth roots, any type of even root, we should consider the plus or minus.
So if it doesn't have that, x is greater than 0.
Then you would need the plus or minus. On the back of the review here, again, I'm going to look at a couple of problems that are here, a couple that I'm going to edit. I want to edit number 20. Instead of the function that's there, I'm going to do a negative 2 square root of x minus 5. So the first thing we want to do when graphing one of these is think about any shifting that occurs. What does that minus 5 do to this graph? Goes to the right 5. When it is with the x underneath the root, it's going to go side to side, and it goes opposite of what is indicated. So this is going to go to the right 5 spaces. For a square root, that creates our starting point, or our end point. Then we want to make a chart. The equation we use for our chart does not include any of those additions or subtractions because we already took care of those for shifting. There's no shift up or down on this one because there was nothing added or subtracted outside of the parentheses or outside of the root. The numbers we want to use are our perfect square root numbers, 1, 4, and 9. We want to plug them in. Square root of 1 is 1 times negative 2 gives negative 2. Square root of 4 is 2 times negative 2 gives negative 4. Square root of 9 is 3 times negative 2 gives negative 6. Then I want to plot these from the end point. So I want to go over 1 and down 2 from the end point, not from the origin.
Why isn't the endpoint on the y-axis?
Because it was a shift sideways, so it stayed on the x-axis. When it's under the root, it's a sideways shift. Then I want to go over 4, which I don't really have room for, but I'm going to do anyway, and go down 4. So that you want to have at least 3 points on your graph so you can see the curve. Domain and range. Domain deals with x, range deals with y. Where does x begin for this graph? 5, and gets bigger from there because it's pointing out to the right. Where does y begin for this graph? 0, and does it get bigger or smaller? Smaller, so y is less than or equal to 0. The graph will always be pointing to the right, so your domain is always going to be a greater than, but the range could be a greater than or a less than depending on if your graph is pointing up or pointing down. From the end point. So I did that shift to the 5, and then I went from that end point over 1 and down 2. Not from the origin, but from the end point. I want to look at one more graph. I want to do y is equal to 2 cube roots of x plus 1 minus 3. Okay, first I want to take care of any shifting. What does the plus 1 do?
Move it over to the left.
Left 1. What does minus 3 do?
Go down.
Down 3. So I'm going to go left 1 and down 3. A cube root graph does not have an endpoint. This is going to be the middle of our graph.
Wait, how do you know if it's going to be in the middle?
Because it's cube root.
What if it's
If it's a square root, it's the endpoint. If it's a cube root, it's the center. And we didn't talk about any other kind of roots. For my chart, I'm going to use y equals 2 cubed roots of x. In the chart, we want to choose x's that we can take easy cube roots of, which are positive and negative, 8 and 1. If I plug in positive 8, the cube root is positive 2, times 2 is positive 4, and the negative will just give the opposite. If I plug in 1, cube root of 1 is 1, times 2 is 2, and the negative will just give the opposite. From this point, I don't really have a lot of room to go back 8, but I'll go back 1 and down 2, and again, that's from the end point, not from the from the center point, not from the origin. Then I'm going to go over 1 and up 2, and then I'm going to go over 8 and up 4. You want to have at least one of those far points plotted out. If you can't get them both, that's fine, but you want to have at least one of those far points plotted out so that you can see how the graph is flattening.
So what's where do you the midpoint?
The center point is from the shifting, and so that was the first point that I plotted, which is the one that I just highlighted there in green. And that went to the left 1 and down 3 from the origin for the addition and subtraction of equation. And then everything else is plotted from there. Domain and range. Those arrows are pointed forever left and right, and forever up and down. So domain and range are both all reals for a cube root graph. One more problem I want to look at is the last problem, 23. To start, everything in that is trapped underneath a root. I can't do anything with the 4, I can't do anything with the x squared because it's all stuck under the root. So I have to get rid of the root. It's a cube root. To get rid of a cube root, we need to cube. I'm going to cube both sides. Cubing the cube root does not alter anything under the root, it just gets rid of the root. Cubing the 2 is 2 times 2 times 2, which is 8. Then I would want to subtract 4 from both sides. And take a square root. What do we need when we take a square root? Plus or minus 2. Most common mistakes on this problem are trying to do something with the stuff under the root before you get rid of the root. Okay, so make sure you get rid of the root and forgetting the plus and minus. Anytime you take an even root like a square root or a fourth root, no problem, you'll need a plus or minus in front of that. Okay. On number 22, common mistake there, I'm not going to go through the whole problem, but a common mistake is forgetting to divide both sides by 4 at the beginning. Okay, before you raise a side to a power, you want to get that root alone if you can. So we want to get rid of the 4 on both sides of that first by dividing both sides by 4. Okay? Not super messy. Okay, I mean, I'm not guaranteeing that you're going to have all whole number answers, but I try to untest not have problems get disgusting, because I think that takes away from knowing if you actually know the skill or not.